Legendrian Torus.
Great. Okay. Thank you. It's really an honor to be able to present this work. So, but as the last speaker, I thought it would be good. This is a perfect chance to thank all our organizers. So Frederic Bourgeois and Helmut Hofer and Klaus Niederkruger and Soban Sefadini. So I'm sure this wasn't an easy at all conference to organize in this pandemic time. So thank you, thank you, thank you. So must have been very challenging with, will this happen in person or not? And lots of decisions. So yeah, so today I'm talking about some work. It's joint work with Jennifer Dalton and John Etnyre. So Jennifer was one of my graduate students at Bryn Mawr. So Bryn Mawr is near Philadelphia. And so some of the results I'm talking about today are results of her thesis. But then there were some parts that she didn't quite finish in her thesis. And so John Etnyre and I have been working on that off and on for a long time. So we kind of get stuck at a point and then we come back to it a little bit later. So I'll talk a little bit more where the sticking points are. Okay, so just to kind of put it in context. Okay, so here. So a classic problem in topology is just knot and link tabulation. So if you've seen like Rolfson knot tables, these are kind of beautiful pictures where they just kind of try to write out all knots. So for example, this is the zero crossing, which is the unknot. This is the trefoil. And notice they only put like one trefoil. In fact, there's two trefoils. So they usually don't draw these tables where they list the mirror images. And sometimes those mirror images are the same. So that's really beautiful. And they also, you try to generate like families of knots, twist knots, torus knots. And so what I'm really talking about or thinking about is like a tabulation of Legendrian knots and links. So I'm working with a standard context structure and Legendrian curves. There's been lots of nice, much more beautiful pictures of this. So just working with the standard context structure, and our Legendrian curves are just always tangent to this distribution. So I really loved Alvaro Del Pino Gomez's talk, so his video of that, I was very jealous of this. So again, we want these curves that are always tangent to these contact planes. Usually I'll be drawing them in terms of the front projection. So they'll have these cusps and they'll be sitting in the XZ plane. And these cusps are just a fact of the projection. So it's just that, I'm just looking at it from a particular angle where it looks like it has a cusp, but if I twist it a little bit. So these are really smooth. So I'm just always listing with the slope condition here. And if you're not used to dealing with a lot of Legendrians, often just keep in mind that the nice advantage of the Legendrian is that we don't have to say which strand is over and which strand is under by a broken line, which is traditional in topology, because the slope tells us which is over and which is under. And to keep a right-hand coordinate system, the y is into the board, so like the lesser slope is always on top. So they all crossings always look like that. So a basic property is that every smooth knot or link has a Legendrian representative. So again, that kind of goes back to the ideas that Alvaro was talking about in his talk. But in fact, there has an infinite number of different, up to Legendrian isotopy, Legendrian representatives. So we're interested in two Legendrians and can you get from one to another through a one parameter family of Legendrians. So there are two classic invariants that I'll label as the TD, which is the Thurston-Bennequin invariant and the rotation number. So for example, here are just different Legendrian unknowns. So I've drawn it in the front projection with the cusp picture. And then this is another classic projection is the Lagrangian or the XY projection. So you can see that these have nice smooth pictures. And what I've done here, so this is kind of like one Legendrian unknot. And if I introduce these zigzags, that's always going to change the classical invariant. So adding a zigzag up or down is always going to, whether you go transverse it down or up, you're changing the TB and the R. So these classical invariants are very easy. In this other projection, it would just be the rise. So you count with crossings, every crossing has a sign, you just sum up those signs, or you measure the rotation number of a tangent vector. So very easy classical invariants. So you realize that, so when you're thinking about Legendrian knot tabulation, you realize that every knot type has an infinite number of representations. So it becomes like, the question is, do we understand all Legendrian representatives of a fixed smooth knot type? Again, so sometimes we do. So for example, we understand Legendrian knot. Okay, so and it isn't even that long that we've understood Legendrian knot. You know, so 96 Eliashberg and Fraser. So even though there's an infinite number, you can structure that infinite number so you can kind of see the pattern. So in fact, I think of this as like a family tree. There's like one ancestor here, the unknot. This is that unknot with just TB equals -1, rotation number 0. And everything else is a descendant by adding zigzags. So we just kind of say, I get this, I add a zigzag this way. So, and here's the other projection. So even though there's an infinite number, we can kind of see the structure of all the Legendrian knots by drawing these trees. And usually it's a graph, technically a graph. So this is typically how we will draw what we call the graph or the mountain range. I still tend to call it family trees sometimes. So this is, again, each dot is representing a shape. And it's really important to know the shapes at the top. And then everything else just is obtained by zigzag. So there we understand the Legendrian knot tree. So we understand a few more knot types. We completely understand their trees or their mountain ranges. So this is in the area of torus knots. So the knot is an example of a torus knot. So in general, we'll have a torus knot, we'll label it by P and plus or minus Q. P is talking about how many times it wraps in longitudinal direction, and Q is kind of the twisting, like so positive or negative. So the 2 + 3 is just the positive trefoil. And so 3 - 7. And although you usually don't do this when you're thinking about torus knots, but it's going to come up when I'm talking about torus length. When P is equal to 1, you just get an unknot. So again, these are all these smooth knots. By smooth isotopy, you can put them into one of these configurations. So in fact, we understand all the Legendrian torus knots. Okay, so here's an example. Here's a positive trefoil. Here's how a smooth topology. We would write a smooth picture. But if I want to understand all Legendrian representatives, I can think of it as this tree and the mountain range tree. So again, it's mimicking what we saw for the unknot in that there's only a single peak. And in general, for every knot type, there's always going to be an upper bound. So there's always going to be peaks, one or more peaks. And then, so this is like the ancestor of all the Legendrian trefoils. So once I understand that shape, I can understand all of the other Legendrian representatives. So this is done by Etnyre and Honda. And in general, for any time it's a positive torus knot, it's going to have the same shape of a mountain range. There's always going to be a unique peak, and the height of the peak will depend on P and Q. And the mountain ranges are always symmetric with respect to rotation. So you're just changing the orientation will reverse the rotation number, negate rotation number. So again, when I'm drawing this, so in some sense, this mountain range is just recording all the different Legendrian representatives. And this kind of mountain range is, they're simple in the sense that the TB and R will determine all the different Legendrian representatives. So every vertex is representing a different Legendrian trefoil in this case, but in general, a P plus Q torus knot. And they're related, the lines are by the zigzag relation. So the positive trefoil mimics the unknot shape of the tree. But when you do negative torus knots, you can get much more interesting shaped mountain ranges. So here's the mountain range for 3 minus 7. This will have 4 peaks. Okay, so I've drawn the picture of 2 of the ancestors here. And by reversing the orientation, I'll get the other 2 peaks. So in general, you'll get lots of different shaped mountains as P and Q vary. So it depends on the ratio. If you look at the slope, minus Q over P, if you put that between minus M and minus M minus 1, that's telling you that the mountain range will have 2M peaks. And all those peaks, we know what the rotation numbers, the TBs are, and also the rotation numbers. So again, beautiful work by Etnyre and Honda. So this completely understands the mountain range for every negative torus knot. Okay, so now moving on to torus links. So a torus link, well, here let's start with an example. For example, if I looked at a 4 plus 6 torus link, we tend to pull out, I'll tend to pull out the greatest common divisor of 2, because that tells me that there's 2 components. Each of components is a 2 plus 3 torus knot. So the 4, 6 has 2 components, each of which is a positive trefoil. So here's a picture. So in general, yeah, so here's a picture of the 4, 6. But it's kind of like the same construction that you would have done to make the torus knots. It's just when they're not relatively prime, the factors, you get these links forming. And here now the goal is just to understand all Legendrian Torus links. And so that will take a little bit to explain because there's a lot of sub questions, but we want to classify all the Legendrian Torus links. So that's kind of like a little introduction. Now I'm going to move into saying some statements about the classification statements. So again, when you're dealing with links, there's a lot of sub questions. There's like realizability and simplicity and symmetry questions you can examine. And then I'm going to talk about how this can be generalized to cable links. And then at the end, I'll talk a little bit about some of the proofs. Okay, so let me start with just the classification statement. Oh, I forgot to share my slides. I was going to do that. I think now that I'm in it, I can't. So, okay, sorry. I will share my slides later. So, good. Sorry. So the first question is just the realizability. So remember, if you have an, I'll call it NP, NQ torus link, that has N components, and each component is a PQ torus knot. So for example, if I'm looking at a 4, 6 torus link, each component is a torus knot, or a 2, 3, or a positive trefoil. So you can wonder each component, so I can choose a 2 tuple of vertices on the 2, 3 tree, and you can wonder, can I realize the 4, 6 where the components are realized by that pair of vertices? In other words, can I realize the TB and R given by those vertices for each component? Or for example, if I looked at a 6 minus 14. Okay. So it turns out that those 2 vertices that I chose for the 4, 6 can be realized, but this pair of vertices over here for the 6 minus 14 cannot be realized. Okay, so in general, okay, so in general, if how do we know? I kind of think of these like checkers. And basically what we want to be able to do is move the checkers up, and they have to have a common ancestor. Okay, so if you're either where the components are positive torus knots, or if they're negative and not, but not an unknot, then that tuple, you can construct it. That tuple can be realized the torus link if and only if they have a common destabilization or common ancestor. So for this 6 minus 14, this is a problem. But if I move that second vertex down, now I can kind of move my checkers up so that they have a common ancestor. So you can see that because of the shape of the positive torus knot, there's really no obstruction there. So you can choose for any, if you're on a positive torus link, you can realize anything. But for the negative torus links, this becomes there's obstructions here. Okay. So is that making sense, hopefully? And in particular, the max TV reps are given by an n tuple of a peak. So I'll tend to draw circles around these vertices on the mountain range. So that just means I'm choosing that component a number of times. So what's interesting though, is when you have unknotted components. Okay, so if you have negative torus links with unknotted components, so for example, if I looked again, when P is 1, that's an unknot. So if I'm looking at a 2 minus 4, that's a torus link where each component is an unknot. And you could ask, okay, so these are 2 vertices on my unknot tree. So I have a TV minus 1 and a TV minus 2. Can I realize it with that pair? And in fact, no. But you could realize it with these pairs. Okay, so you could either take what I'll call a 2 copy of a TV minus 2. So there's 2 options there. Or you could do a 1 twisted copy, 2 copy of a TV minus 1. So then you have 1 component with TV minus 1 and 1 component with TV minus 3 with the same rotation number. And in fact, these are the ancestors. These are the ancestors for all in this case. So you have your checkers or you have your circles. You need to be able to either move to like an n copy configuration or to these T twisted n copy configurations. So let me just draw a picture a little bit more. So for example, if I'm doing a 2 minus 6, you're going to have 6 ancestors. 3 of them are just by 2 copies on TV minus 3. And then I'll have like a 1 twisted of a TV minus 2 or 2 twisted of a TV minus 1. And these are the pictures down below. So here I just think you can think of it in terms of their graph. And here you have their front projection. So all of these ancestors have max TV. But if I do 3 times minus 1, 3. So again, I have the 3 copy ancestors, and then I have the twisted copies. So in fact, so everything, so there's kind of like 1 can rise, but the other 2 fall. These are all the ancestors. So you have to be able to move your dots, your checkers into one of these configurations by moving up. Only the ones in the bottom row have max TV. So that's kind of interesting. I don't think we've ever had examples of links which do not have max TV but do not destabilize. So yeah. So it's a nice new phenomena coming up with these torus links. Okay, I should make sure this is a good little point to pause. So that's kind of like realizability, like which pairs can you realize? Okay, good. Okay, so now you wonder, now we kind of know existence. So that's kind of realizability is basically an existence question, which pairs or which n tuples. Again, just for exposition, I'm usually focusing on 2, but in general, we do this for n, which n tuples of vertices can be realized. And first, I'm just thinking as an unordered pair. So to illustrate, for example, if I look at 4, 6, could I know I can realize it with this pair of red circles, okay, with where one component has TB 0 and one component has TB -1. Could I realize it? Could there be 2 different Legendrian links that have the same TB and R? And no. So any n tuples represents at most 1 if you don't care about the ordering at all. So, okay. So it's not really an ordering question for this problem, but we'll get into a case where you do have ordering. So this is just kind of saying it's simple. So the TBs and Rs will, as long as you know the TB and R of the components, each of the components, then you know the link. But the really cool question is about the symmetry. So if you have a torus link, then you can permute any of the components by smooth isotopy. So you can kind of think of this, you're on your torus, you just have a component, you just lift it off the torus a little bit, move it around and put it back down. So it's easy to see that there is a lot of symmetry. You can just arbitrarily permute the components in the smooth world. So this is a good time to test like the flexibility and rigidity. Do we still see that, do we still see that arbitrarily permute, or are there cases where there's more rigidity? So for example, here, I'll just look at a 3 copy where each component is a positive trefoil. So this is a 6, 9 torus link. And you can ask, well, can I do a cyclic permutation? Can I do 1, 2, 3 going to 3, 1, 2? So what's really interesting is to break it down between cyclic permutations and non-cyclic. So here I've drawn sort of a front projection here. So cyclic would just be kind of move the black to the red to the blue to the black, so it's kind of cyclically permute. But non-cyclic, you fix one of the components and think of permuting the other 2. And well, sometimes you can arbitrarily permute, and sometimes you can't. So that's what has been very interesting. So in particular,
I have a question. So when you want to do this permutation, do you want the whole isotopy to fix the 3rd component or only the time one?
Only the time one. Yeah. So only at the time one. Right. So here, so cyclic, yeah. So basically we have the link, we kind of move it around and we get back to that position. So in general, cyclic permutations always produce equivalent links. So that's good. But the non-cyclic ones are interesting. So if you're in the positive torus link, that will always produce equivalent. So the positive torus links are very, very flexible. They're mimicking what's happening in the smooth world. You can do cyclic, you could do non-cyclic. If you're in the negative torus link world, if you're not at the top, if you're not max TB, then you can also do any sort of permutation you want. You can do cyclic, you can do non-cyclic. So staying off of that, as long as I haven't chosen the mountain peak end time, you can do whatever permutations you want. But if you're at the top of the mountain peak, then if you choose that mountain, but you max TB, you'll produce non-equivalent max TB ones, so non-cyclic ones. So you can do cyclic, but not non-cyclic. And this is extending some work of Mishachev. Okay. So actually what Mishachev was really, okay, so here's kind of like a different vision of what Mishachev. was talking about, he was usually dealing with where P was 1. So for example, let's take the 4, -8 torus link. So each component is there's 4 components, each is an unknot. If you're in the max TB case, for example, the max TB case here would be, for example, a 4 copy of a TB-2 unknot. You cannot do the non-cyclic permutations. But if you're in the non-max TB, so for example, I take one component has TB-1 and 3 components that has TB-3, then you can do any permutation. You can only, again, when you do the permutation, you have to preserve the classical invariant. So it only makes sense to talk about the permutations of the TB-3 component. But you can do all the permutations you want here. So. Okay. And these results, so hopefully, is that any questions? Is that good? So, okay, let me just say that a lot of these results have extensions to cable links. So you can think of torus knots or cables with the unknot, remember, because these are kind of set in a standard torus. But to make a general cable knot, we just fix an oriented knot type K, and we form a torus neighborhood of that. And then we construct a torus knot on that twisted torus, this non-standardly embedded torus. So there's an example of a 3-2 cable of the trefoil. Okay. So in fact, we also have a classification of all these cable links under some conditions. So if K is a simple and uniformly thick, and I'll say what that means, then we understand all the ordered and unordered classification of all the Legendrian representatives. So it takes a lot to actually write that down precisely. But what that is saying is, though, from P and Q in the mountain range of K, we can determine the mountain range of the cable. So again, we know which this existence, we know which tuples, n tuples can be realized. And we know which permutations can and cannot be obtained by Legendrian isotopy. So simple in this case just means, and going back, so again, it's not all cables, Legendrian cables, but if K is simple and uniformly thick. So simple just means that the TB and R classify all the Legendrian representatives. And the uniformly thick, that's kind of coming from the sense of convex surfaces. You want any solid torus with a core can be expanded to one that's geometrically nice. So geometrically nice in the sense of convex surfaces. I'll say a little bit about, towards the end, I'll talk a little bit more about convex surfaces. And as examples of this, you could do, like, for example, simple and uniformly thick. You could think of the figure 8 knot. All negative torus knots are also in that region satisfied. So just to make that, yeah, rather than to try to do the mountain ranges, I thought it might be kind of interesting just to illustrate this, a little case where K is, let's say K is the figure 8 knot. So then for every P and Q and every N, for every P and Q, you can talk about the cables of the trefoil of the figure 8 knot. And the shapes that you get for the ancestors depends a lot on whether the slope is equal to, greater than, or less than the max TB. So for example, for the figure 8 knot, the max TB is -3. So if I look at the slope, if I look at the 3 component slope -3, I just get this n copy of the figure 8. When the slope is greater, so -5/2 slope, I get this sort of, this is an example of an ancestor. When the slope is less, I get this sort of, this ancestor. And you can see these bigger than or less than is kind of mimicking the constructions that we saw when we constructed positive torus knots or links or negative. And what we find, for example, for the figure 8, if that slope is actually equal to the max TB, you can't do any permutation. So not cyclic, not non-cyclic, there's no permutations possible. The positive ones are mimicking the flexibility of the positive torus links. You can do any permutation. And the negative ones are, again, negative is kind of like less than max TB. Again, we're seeing only cyclic. So in fact, the fact that there's no permutations of the n copy of the figure 8, that was actually already known by Ng, but this is kind of a way to, a lot of these results are kind of crystallizing and pulling together a lot of previous known results. Okay, so now I'm going to move on to the proofs a little bit. Okay, so when we're studying these links, it's kind of an interesting problem because you can approach it from different techniques. So in general, when you're studying Legendrian submanifolds, we have lots of different techniques. One of my favorite techniques was the generating functions. So via the generating functions, which is really analysis and Mawr's theory, we can show that you cannot do non-cyclic permutations of the n copy, or n minus n. So this was realized by Mishachev. And I just thought I'd give a little outline. This is more technical for those who understand the generating families. I'm going to focus more on the convex surface arguments, but the idea here is that if you look, so the generating families, they work really nice for one jet spaces. And so if you look in the one jet spaces of circle, this is an argument I did a long time ago, you could see that these two, this is a Legendrian link. So I'm representing the circle as a quotient of the interval. So this is actually a circle. These are two Legendrian circles, the red and the green. And you can show that you can't swap those circles. So by a Legendrian, there's not a one parameter family of Legendrians that will take the red and the green to green. And then Mishachev realized, and Ding and Gygas kind of wrote this up carefully, is that implies that you can't do this non-cyclic permutation of that torus link. So you just embed the one jet space of the circle into S3, and then you just add on. So basically that's kind of the idea. So those links, you can see those non-cyclic permutations are impossible using the generating family. But at least I don't know how to do that for other ones. So you move on to like the holomorphic curve techniques, the DGA. So in fact, with this technique, you can show that you can't do non-cyclic when P equals 1. So if you're doing n copies of an unknot, okay. So again, but not at the top of the mountain, but these other ones. So it's n copies of any stabilized unknot, you cannot do the permutation. Mishachev, this is Mishachev's idea. So again, this won't be the focus of it's not the focus of what we did, but here I'll just kind of outline some of the ideas that Mishachev did. So the idea is, well, you look at one of these unknots and it doesn't have an augmentation. So so the DGAs, we kind of like to have these augmentations. In fact, if you look at the 2 copy of this unknot, it'll have a unique augmentation. And then you can look at the 3 copy of the 2 copy, and then there's this characteristic algebra that you can form. And Mishachev showed that in some cases, so if you did a kind of labeling, doing your labeling, one time this characteristic algebra has a 0 divisor, and the other time it does not. So Jennifer Dalton, so she spent a lot of time in her thesis trying to extend this, and it was hard. Okay, so when P equals 2, you still have you can still work with like unique augmentations, but it turns out both of those characteristic algebras have 0 divisors, even though it doesn't look like it. I mean, these are fairly hard these are lengthy sort of calculations. And at first it looks like, oh, one doesn't have a zero divisor. And then you realize, oh, yes, it does, so it's just the algebra. So with more modern sight, we've been able to realize that, oh, when P equals 2, you can use kind of like the idea of the product structure. So I think you could do the DGA for P equals 2 for all the torus links there, DGA sort of approach. But when you get to P equals 3, the number of augmentations just sort of explodes. I mean, you start to have like 3 basic ones and then the 3 copies. So you're talking about 27 augmentations, and then those are the minimal ones, and then there's other ones, and it just kind of like it gets. And then for each of those 20, at minimum 27 times, you'd have to calculate characteristic algebras, and so we tried for a while, different sort of augmentations and a whole bunch of things, but in the end, we were able to do it with convex surfaces. Okay, so this convex surface has worked really well. So for showing things are equivalent, and actually to show that you can't, you're getting obstructions. So all the results I mentioned today about the classification Legendrian Torus knots by Etnyre and Honda, that was done with convex surfaces, and all the results about the torus links and the cable links, this has all been done by convex surfaces. Okay, so let me just say a little bit about the techniques. So in general, when we have a surface inside our contact manifold, we have this characteristic foliation, and that's very powerful, but very delicate. So the idea is to work with these convex surfaces. So there's a transversal contact vector field. You want to I think of that as a perpendicular to your surface. And then on your surface, you can kind of measure, well, when are my contact planes perpendicular? Then you get your dividing curve. So this is extending, going down in dimension from what Russell was talking about. So here, so you just kind of measure where is the contact plane perpendicular. That gives you your dividing curve. Your Legendrian divides are where your contact planes are tangents. So these are actually singularities. So you get these curves of Legendrians, Legendrians formed by curves of singularities of your characteristic foliation. Then you also have your Legendrian ruling curve. So it turns out that even though the characteristic foliation is very, delicate, these dividing curves are very robust, and they give you a lot of information. So let me just give an example of how we can use some of the convex surfaces. This has really been I'm a novice at this convex surface technique, so it's been really interesting for me to think of this way. So I would tend to think of things in terms of the front projection. So if I wanted to realize a negative torus link, years ago, I think of a front projection, but this is sort of like the convex surface way of thinking of negative torus links or torus knots. So say I want to realize the ancestors of the negative torus link. Say P is not 1. So remember the ancestors, there were these multiple peak mountain ranges, and you would choose the top vertex a number of times. That was one of your ancestors, n times. So first, depending on the slope, minus Q over P, okay, if it's between minus M and minus M minus 1, I would just start by choosing an unknot, the TV minus M. And there's going to be M choices there. And then inside a standard convex neighborhood of this unknot, there's these basic slices. So if you're familiar with the Fairy tessellation, you can think of so this is a way of, we draw this Fairy tessellation. I think of a basic slice here as 2 points in the Fairy tessellation that are connected by a geodesic. And actually, you can assign a plus or minus sign to each of these geodesics, and that's giving you 2 choices. Okay, so, and then once you have this basic slice, we know that there's a pre-Lagrangian torus in there of that slope. So this is so this torus, the characteristic foliation is non-singular, and it has slope minus 2 over P. And then just choosing n of these lines will give you an ancestor. So that's where you're seeing, remember, if you, for these negative torus links, remember there's often multiple peaks. It's like 2 M choices, but you can kind of see there's M choices for the unknot, and then 2 choices for the basic slice. And then after that, you're just choosing these this torus, this pre-Lagrangians here. So to give you let me give you an outline of how so that's how you can realize these ancestors at the top, these multiple, choosing a one vertex multiple times. And how, I'm just gonna outline how you can show that you can't do a non-cyclic permutation. Okay. So if it sits, so we know that this torus link sits on a pre-Lagrangian in one of these basic slices. And the idea is, well, if I could permute 1, 2, 3 to 1, 3, 2 in R3 or in S3, we could do this in a basic slice. So that takes a fair amount of argument to show that, but that's kind of the idea, is to kind of localize to this basic slice. And then we argue that we just have a lot of S1 actions. So instead of thinking of this T2 cross I, I'll just think of this as an annulus cross S1. So this now instead of my components, I'm just representing as dots here now. So the S1 coming out of the page is representing the dividing, so the slope and everything. So we're just translating this to working with an annulus cross S1. Okay, so I just recopied the argument, so to continue. And then the idea is, if you could do a permutation, then there would be this, that I'm going to actually take these components, I'm going to look at a little neighborhood, and there's a lot of arguments, topological arguments to argue S1 invariance, but basically I'm going to show that I can have a 3 punctured annuli. So work instead with punctured neighborhoods here. And if I could do this non-cyclic permutation, then I would find the existence of 2 different annuli, A0 and A0 prime, in this A0 cross S1. And A0 prime would be isotopic relative to the boundary to A0, but the dividing curves are not isotopic relative to the boundary. So again, we're trying to use sort of the rigidity of the dividing curve to detect rigidity here as an impossibility. And in fact, this violates a proposition of Honda, this uniqueness of minimizing configurations. This is a proposition that I used in the classification of tight contact structures on surface cross S1. So there's a lot. So basically, we're just detecting the cannot do those non-cyclic permutations by the existence of this here. Okay. So just as a summary, I just want to hope that takeaway messages are that Legendrian torus and cable links, they exhibit interesting flexibility and rigidity. So sometimes they're behaving just like the world of the smooth world, but sometimes different. And I've just been really impressed by this convex surfaces, a powerful tool for showing that Legendrians are equivalent and are not equivalent. Okay. So here, if we, yeah, it's interesting. We haven't really introduced a lot of new machinery, but it's just kind of a matter of finding the right machinery from machinery that already existed to solve this problem. So, okay, thank you.
Is there any question?
So I think this is interesting. So the machinery is not new, but maybe you're using it in a new way. What sort of made you think, oh, we should kind of revisit this, or maybe there's some more juice to squeeze out of the lemon, or maybe a new way to think about it. How did that happen?
Yeah, painfully and slowly. Yeah. So so I think yeah, it took us quite a while to I mean, it took us quite a while to think of ways to kind of approach this question, you know. So yeah, so we just kept trying, you know. So first we kind of realized that we could do some things in the basic slice. You know, I can't tell you how many times. I mean, we've been working on this off and on for over a decade. You know, we kind of start as like, oh, we can do p equals 2, and oh, we can do this, you know, these rotation numbers, you know, and then finally just realizing, okay, we could get it in the basic slice, but then realizing that we could kind of localize that basic slice. And this, yeah, it just took a lot of effort. Yeah, so. And again, John was very influential in this. I'm much more of a newcomer to this area of convex surfaces. So, and it was hard also because the result of that we're using of Honda, it was kind of like embedded. It's not like the main result, but just kind of a proposition that he was using to prove his main result. So, yeah, thank you.
If there is no other question, we can thank Lisa again. Next week, we put again the link of the data in the chat in case some people want to meet there. And goodbye.
Okay. Thanks, everyone. Thanks for the talk, Lisa. Non, je n'étais pas. Ouais. Il y avait un bref, ma tête, je sais pas. J'avais pas cette question.
Merci pour la conf.
Ah, de rien.
C'était super.
Ah, voilà. Dan, made it.
I did.
Wow, I thought you'd be sleeping or something.
Hello, Dan.
Hi there. Hi, everybody. Hi, Marco. Good to see you.
Where's the baby?
Good to see you, indeed.
Yeah.
Congratulations again.
Thank you. Yeah, it's pretty exciting.
Yeah,
Yeah.
I'm sure. Yeah, I know. Say hi to Julia.
I will. She's doing well.
You guys are still in Rhode Island?
Yeah, that's right. That's right.
Hey, so the name is Layla, you said?
Lila. Actually,
It's not
we
like
spent a
Star
long
Wars.
time debating Layla versus Lila. We spent a long time debating Layla.
So, but you write it with so L-I-L-A or something like that?
Lila. Yeah, that's right. That's right. We spent a long time debating the spelling too. We had to actually send away the
Layla?
what?
How do you know you're? Is it clear that reads as Lila and not Lila?
Well, I think it's sort of up to Lila, and the listener to decide. I mean, if the listener wants to call her Layla, that's okay too.
Fair enough.
Our role. I mean, I don't know how it works in France, but you have to, write down the name close to the time of birth, or else you have like an infinite amount of paperwork to do later in life or something.
Oh yeah. That I know. I know.
We had to write down. We had to actually send away the paperwork people twice while we debated.
Okay.
Okay, we are recording this conversation. Which is